Have you ever just stared at a calculus problem and thought to yourself, there is no way. This is literally impossible. Well, today we're going to unlock a technique that honestly feels like a magic trick. We're talking about power series, and trust me, they are the secret weapon you've been waiting for in your mathematical toolkit.
You know, when you're a calculus student, you're constantly running into these functions that just refuse to play by the normal rules. So what do you do when all the standard methods fail? That's the big question we're going to answer today. Yeah, we're talking about those integrals that just don't have a nice, neat solution, or those differential equations that look more like an unsolvable puzzle. This is the wall that so many of us hit. But what if there was a way to just sidestep the problem entirely?
So here's our game plan. We'll kick things off with the big idea behind power series. Then we'll learn a foundational trick, see how to expand on it, and then put it all to the test with a classic example. And finally, we'll talk about what this new power really means for you.
Okay, let's get right into the core concept. What exactly is the secret weapon?
I know. That definition sounds a little dense, a little academic. So let's think about it another way. Just imagine you could take any complicated function, I'm talking logarithms, trig functions, whatever, and just rewrite it as a simple, infinitely long polynomial. That, right there, is the promise of a power series.
This quote just nails it. It's the core of the magic trick. And why is this so incredibly powerful? Well, because polynomials are basically our best friends in calculus. You can differentiate them, you can integrate them, you can plug in numbers. It's all just basic arithmetic. So if we can turn some monster function into a friendly polynomial, we've pretty much already won the game.
So, how do we start performing this magic? Well, every great trick has a simple foundation, and for us, that's the geometric series. Think of it as our one solid link between a simple-looking fraction and an infinite polynomial. It's the key that unlocks everything else.
This formula right here, this is our Rosetta Stone. It is the one power series we take as a given, and it lets us find countless others. All it says is that for any x with an absolute value less than 1, the function 1 over 1 minus x is exactly the same as the infinite sum of x to the n. You've got to remember this one. It's the foundation for everything.
And what's really cool is how simple the trick is. You just take our base formula and you can substitute pretty much anything you want in for x. So for example, if you want the series for 1 over 1 plus x squared, you just think of it as 1 over 1 minus negative x squared. Then you replace every x in our summation with that negative x squared, and bam, just like that, you've got a brand new power series.
Okay, substitution is powerful for sure, but that's just the beginning. Now we're going to bring in the full force of calculus to really level up.
This is where it gets really amazing. Since a power series is just an infinite polynomial, we can do calculus to it just like any other polynomial. We can take the derivative of the whole series or the integral of the whole series just by doing it to each little term one by one. This is how we can build series for functions like the natural log or arctangent from the ones we already figured out.
Now here's the crucial detail that makes this all mathematically sound. When you differentiate or integrate a series, the new series you get is still valid over the same range of x values. This is the guarantee that allows our whole method to work reliably. It's a huge deal.
All right, enough theory. It's time for the payoff, right? Let's put all these pieces together and use our new secret weapon to find the power series for a really useful function, arctan of x.
So here's our strategy. We don't know the series for arctan of x directly, but we do know its derivative. And that derivative, 1 over 1 plus x squared, well, that should be looking very, very familiar by now.
And there it is. This is the exact function we found just a few minutes ago using our geometric series trick. We've already done the hard part. We know the power series for the derivative of arctan of x.
So now we just reverse the process. To get from a derivative back to the original function, what do? We integrate. And we can do it term by term just using the basic power rule over and over again. And of course, because we integrated, we can't forget our old friend, the constant of integration, plus c. We are so close.
This is the final touch. We've got to find the value of c. The easiest way is to plug in a value we know. We know for a fact that arctan of 0 is 0. So if you plug x equals 0 into our new series, what happens? Every single term with an x in it just goes to 0. So we get 0 equals 0 plus c, which means c has to be 0. Easy enough?
And there it is. We actually did it. We took the arctan function, something that's not a polynomial at all, and represented it as an infinite polynomial. This is huge. Now we can use this to get super accurate approximations for arctan, or even to integrate functions that involve arctan that seemed impossible before.
This is an incredibly powerful result. Think about what we just did. We started with one single, simple formula. And from that, we built a tool that can take apart and rebuild these really complex functions. That power is now in your hands.
So just think about it for a second. We used this trick to unlock arctanx. We could have used the exact same method to find a series for, say, the natural log of 1 plus x. What other impossible functions could you tackle now? What integral or differential equation that seemed hopeless before could you now solve by turning it into an infinite polynomial? The possibilities are out there, waiting for you to find them.